Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome everybody to today's MSR colloquium. We're delighted to have Chris Moore, previously of University of New Mexico and for the last few years at the Santa Fe Institute. Chris wears many hats: mathematician, physicist, theoretical computer scientist, and today's talk will be sort of a fusion of all those personae. He's also written a very engaging and popular book, The Nature of Computation, assuming I'm getting the title right. And we're very delighted to have him here. If you are not going to the retreat Wednesday and Thursday, and you want to see more of Chris, he's going to be coming in tomorrow morning. So, all right. And with that, I will turn it over to you, Chris.
Thank you very much. So I've had the honor of working with lots of great collaborators, people who've taught me a lot. I know that not everyone here is a professional theorem-proving theoretical computer scientist. For those who aren't, then I hope there'll be some nice lessons here about how we can infer things from data and when we cannot infer things from data. And for those who are, there'll be lots of good conjectures here for you to prove. All right, so I want to push a certain analogy between statistical inference and statistical physics. And physics and computer science are both about lots of things that are interacting with each other. At least that's what statistical physics is about, and about the global behaviors that emerge from them, whether those are natural systems that we try to understand in physics or engineered systems that we're trying to design to get an algorithm to work. So I think the two fields, as many people here know, have a lot to say to each other. So let me first philosophize a little bit, since it's the afternoon. We're all looking for structure in data. What does that mean? How do we know when we've found it? So one thing is that structure is what makes the data different from noise. So if you have some simple null model, some structureless background model, it's what makes the data different from that. So in a graph, you could have a really simple random graph model, and you could ask, to what extent does the network in front of you differ from that? Another point of view is that structure is what lets you compress the data. So if I have a huge network and you want me to send it to you.
Chris, there are examples like Samaretti's lemma, which say that even when you think it's noise, they're actually a structure. But anyway.
That's true.
Yeah.
Yes.
So you can't avoid structure. Yes.
And we'll talk about that. But if structure that you can't avoid is not structure. I mean.
I'll let you fight with Terry Tao and Samaretti on that. But
No,
anyway,
well.
No. Yeah, I'm sorry. I should not have randomized you.
Structure you can't avoid. Structure you can't avoid. You can exploit for algorithmic purposes, which is great because then it's there even in the worst case.
Right.
But it doesn't. If you see it, it doesn't mean that you've discovered some pattern in the data because it would be there no matter what the data was.
Yes.
Good. All right. All right. Another attitude about structure is that what lets you compress the data. You don't want me to send you the raw adjacency matrix of a million by million, of a graph with a million nodes. You want me to give you some succinct description of it, either exact or inexact. Informally, you want to know what are the important structures, and of course that's application dependent. So one very good test for whether you've actually found something in the data is whether you can extend what you know about the data to what you don't know. So based on a past time series, can you say anything about its future? Based on some of the links in a network, can you say anything about the ones you don't know about? Here's one I wanted to throw in. So my friend Jennifer Dunn at the Santa Fe Institute is an ecologist, and she's studied food webs, including fossil food webs that are hundreds of millions of years old and reconstructed from I guess, teeth marks in fossils. I'm not sure how it works exactly. She wants to know whether evolution has merely changed the individual species that live in the ocean, or whether the overall structure of the food web has changed in some way.
What's a food web?
It's, you know, nodes are species, and an edge is this eats that. Yeah.
Chicken is under you, and I don't know. Lion
Yes.
is above you.
Is your slide contradicting itself in the sense that
I certainly
if
hope
your
so.
if your friend found that food webs ever since the Cambrian have been indistinguishable from GNP, that might be a very successful structural finding.
That would be
in one
terrible.
context, but
Well, so, I mean, for instance, have the number, ecologists try to figure out why do food webs have a certain number of trophic levels, from plants to herbivores to carnivores to super carnivores or whatever. Why aren't there 17 layers, for instance? You know, what does that have to do with the amount of resources? And I don't know. But I like putting this up here because it's not a math question, and I'm not sure how to turn it into a math question. So far I have not been able to help her very much with this question. So it's a challenge, bridging between the science and the math. Finally, we're interested in a lot of dynamical systems on networks, oscillating voltages in a power grid, epidemics going through various communities. Perhaps one thing structure can do for us is give us a useful coarse graining of a dynamical system, like when epidemiologists say, I don't want to think about a 7 billion dimensional system to model my epidemic, and I don't have that much information anyway. I'll just assume there are 20 kinds of people, like 70-year-old Estonian women and African-American college students, and there's a 20 by 20 matrix of transmission rates. So I'll treat it as a 20-dimensional system. So if there's something going on in a network and we can divide the nodes into communities, then maybe it gives us that kind of coarse graining, that lower dimensional approximation. All right, so I have fallen, I have the zealotry of the recent convert for this approach to all this broadly called statistical inference that many fields have rediscovered. The idea is you have some data in front of you, in particular a network. For most of the talk, a network will be a graph. But of course, networks are much, much, much more than graphs. But let's pretend they're just graphs, sets of nodes with links between some pairs. So we're going to assume that it's generated by some underlying model which has some randomness, but also some parameters. And we'll try to fit the parameters to the data. And one reason I like this is it's very happy to deal with partial or noisy information. So for instance, maybe there's some metadata, some attributes, demographics or locations or something that you know about some of the nodes in your network, but not all. Maybe you don't know all the links. So I think because we often think about online networks where someone, at least Facebook, knows all the links, we forget that in a lot of real networks, discovering the links takes real work in the laboratory or the field. One of the networks we've worked on is a food web of about 500 species in the Weddell Sea in the Antarctic. So to discover those nodes and links, someone had to sit in a boat and be really cold for a long time. Also, some links might be false positives, right? So just because two proteins stick together in a test tube does not mean they work together in the cell. Just because two genes have activity levels that are correlated does not mean they have a causal link in the genetic regulatory network. So the data we have is going to be incomplete and partly wrong. Anyway, you give whatever data you have to some procedure that fits the model to it, and then you can take that inferred model and make guesses about what you don't have, and hopefully you get some of that right. All right, so I'm going to introduce you to an old and extremely naive model, but it already has a fair amount of personality and some interesting things to say about it. I think it started in the sociology community. We're going to assume there are k kinds of nodes in the world. There are like 3, red ones, blue ones, and green ones. And now, if you're familiar with the Erdős-Rényi random graph model, that's the most naive model in the world. It just says that every pair of nodes is connected with the same probability p. In the stochastic block model, we generalize that so that there'll be a little k by k matrix, so that if I'm of type R and you're of type S, there's a link from me to you with probability p sub rs. Now, we can model directed links. Predators eat prey and not the other way around. So this matrix does not have to be symmetric. We also are not going to necessarily assume that it's bigger on the diagonal. So in social networks, we're used to the idea that people are more likely to be connected if they're similar. But again, consider the example of predators and prey, or like words in an adjacency, adjacent words in text, right? Adjectives come before nouns in English, and sometimes next to other adjectives, but nouns don't usually come next to other nouns. All right, so there's lots of games we can play. Yes?
Block model.
Yes, that's true. Now, some people write block model without a space, but I resent the gratuitous formation of compound words in English. I think, in German, that's perfectly appropriate behavior, but in English, I think there should be a space. All right.
In German, the title would be Massoulie 2 words.
Yes, the whole thing, yeah. All right, so there are lots of games we can play. I mentioned before that we know maybe we know some of the links and not others, but at the moment, let's say that we do know all the links, we know the topology, but let's say that these types are hidden and you want to find them. And maybe you know this matrix P, but maybe you want to learn that as well. Maybe you don't initially know the likelihood with which group 2 connects to group 7. I'm going to mostly assume that we already know how many types of nodes there are, but of course that's an important question, right? Because if I give every node its own type, I can model the whole network perfectly, but I've learned absolutely nothing about it. So that would be an egregious example of overfitting the model to the data. Anyway, so choosing the number of groups is an important model selection problem. All right, here's a little cartoon. There are 3 groups. This group doesn't like to connect to themselves. These guys really do. These 2 groups like to connect to each other. And so you can imagine a little 3x3 matrix of these edge probabilities. Food webs. So I like this because in most work on community detection in networks, we assume that a community is a clump, that it's more densely connected inside than to the rest of the world. And lots of people, there's a huge literature on that. So here we're defining community in a somewhat more general way. I would say that 2 predators are similar not because they link to each other, because they don't eat each other, but because they eat similar prey. So here you belong to a community with each other if you connect to the rest of the world in similar ways. This could happen in economics. You could have a roughly bipartite network of suppliers and customers. Maybe the suppliers don't do so much business with each other, but they compete for the same customers. We mentioned word adjacencies. Even in a social network, you can imagine competing leaders who are trying to connect to the same followers, but they don't like to acknowledge each other's existence. Maybe you know people like that. Okay, so here is a little picture. This is getting old. I think I need to change it at some point, but these are the 60 most common nouns and adjectives in the novel David Copperfield, and there's a link if they occur next to each other in the text somewhere. I, or rather my student, told the algorithm that it had 3 groups to play with.
So when you say 60,
What?
how come there's a number 101 if it's 60?
There's a total of 60 nouns and 60 adjectives. So it did a pretty good job of putting adjectives here and nouns here. We did not tell it anything about the structure of the English language. We gave it 3 groups to play with, and it used the 3rd group for things that it had trouble classifying. And this include the word light, which appears as both a noun and an adjective in the text. So anyway, it's kind of fun to see what it does.
What's black and what's white?
The black and white are the nouns and the adjectives.
So even up there, those are nouns and adjectives.
There's some of each, yeah. It's by no means perfect. Obviously, anyone who works seriously on part of speech tagging would just laugh at this, but I think it's a kind of nice little example. All right, so of course, fitting a block model to a graph is NP-hard. So for example, graph coloring, where you are only allowed to connect to other people if they're a different type than you, is one of the classic NP-complete problems. So this is NP-hard. On the other hand, don't kill me, but I think this is one of those cases where we don't care. So, I mean, if you're trying to fit a model to data and you're finding it incredibly hard computationally to fit the model to your data, maybe it is the wrong model for your data. So maybe if the stuff you're trying to find is really hard to find, maybe it's not really there. So we can talk about that some more. So in practice, there are several methods that work quite well. I will be talking about belief propagation because it has this nice analogy with physics and because it is also good. There are other methods that can work quite quickly even when you have rather complicated models. There are some variants of the block model that have easier algorithms. We'll talk about spectral methods at the end. But belief propagation is the coolest because it builds this analogy with physics, which is always a good thing to do. And it will also give us, unlike many other approaches, it will give us natural measures of whether the structure we found is really there. So in other words, maybe you could even, I'll give you the magical ability to find the best possible fit of a block model to your network. Well, I don't just want to know the optimum. I want to know, in some sense, how robust this optimum is. And so we'll find that there are some measures of that. And also analyzing the performance of belief propagation will reveal these phase transitions in our ability to find communities. And it turns out that in some cases, we just cannot find them. All right, so let's just write down this model. This part is easy. So if you knew all the types of all the vertices, then the probability of getting the graph in front of you would be really easy to write down. It's just the product over all the edges that exist of the probability that they do and all the edges that don't exist of the probability that they don't. Okay? So one thing is you can try to imagine maximizing this function as by altering the types of the vertices, because again, you're trying to figure out the types of the vertices. I've shown you the graph. Now, of course, in statistical mechanics, in physics, Ludwig Boltzmann taught us that if you're at a particular temperature, then the probability that you're in a given state it decreases exponentially with the energy of your state. Rocks fall, so we prefer lower energy states, but when things are warm, they are occasionally found in higher energy states. So because of this equation, and I'll take the temperature to be 1, although it's useful to tinker with it a little bit, then the first thing a physicist would do is take the logarithm of everything and change this probability into an energy. So when you do that, you get a sum over all neighbors of now this log of the probability, and to the connoisseur, this looks like a generalized Ising model, or if you are a real connoisseur, a Potts model, where, so between each pair of nodes that are connected, there's some energy associated with their combination of types. In a classic magnet, like a block of iron, we would prefer to be the same as our neighbors because we're conformists. And so then this would have a higher energy than that. So here there's just some matrix of energies depending on the types. There's one twist though, which is there are also interactions between the non-neighbors, right? So, I mean, if I didn't know all these people, there had to be some explanation for that. You know? So maybe I've been living under a rock or something. So the fact that edges don't exist does tell you something about the types of their endpoints. Now, in a sparse network, where p is small anyway, these terms are small. On the other hand, there are a lot of them. There are about n squared non-edges and about n edges in a really sparse network. So we can't ignore these terms completely, as it turns out. All right.
Why don't you just multiply it out by all the edges and factor something out?
Well, yeah, you can do that too, right? But then yes, you can do that too. Are
we assuming each term is positive?
Well, but it depends on the types, right?
Oh, right.
Right. It does depend on the types.
It does depend on the types, right.
Okay, so here's a little two-way glossary. The probability of our graph, given these underlying labels, becomes this beta there is 1 over the temperature, becomes this Boltzmann distribution. So it's minus the log probability becomes the energy. Now, the most likely labeling, which, you know, if you've hung out with people who do machine learning or inference, you've noticed that there is a constant hail of 3-letter acronyms, or TLAs. So, you know, I find this very unpleasant, but there's a lot of it, so, you know. Anyway, this is the maximum a posteriori estimate. And
It's the same thing.
it's the same thing. But mode has,
Mode is a real word.
and also mode has only, mode is the disadvantage of only having one syllable, whereas if you say maximum a posteriori, then it's kind of partly Latin and it sounds very fancy, although then people say the map estimate, and anyway, never mind. It's horrible the way this field works, but okay. So the most likely labeling is the one with the lowest energy, and that's what physicists call the ground state. So we can also call this the ground state. So it can also be worthwhile to sum over all combinations of possible types and look at the total probability that we could get the graph out of the model. And this is called a partition function in physics. And if it's also the normalization factor, so, you know, if we actually want the posterior probability, I'm ignoring the prior here, the posterior probability of the labeling given the graph, well, use Bayes' rule and normalize. This gives the Gibbs distribution, which physicists call the Gibbs distribution. Finally, minus the log of this is the free energy, which I will argue is a kind of good measure of the overall ability of this model to fit the data.
What do the statisticians call that?
I think they call it the free energy if they've heard of it. Maybe there's something else. The marginalized, maximalized, normalized, regularized, I don't know, something. All right. We're getting punchy here, that's good. All right, so now, your friend the biologist or your friend the sociologist has a network and she wants you to tell her what the labels of the nodes ought to be. So what's the best one? Well, one thing you could do is take that maximum a posteriori estimate. The labeling which maximizes the probability of the graph. But this is wrong. It's wrong. It's a terrible idea. Bad. Why? Because of illusory communities that are not really there. So, for instance, here is a graph. I have labeled the vertices. I put the blue ones on one side, the red ones on the other, and only about 11% of the edges cross from one to the other. So clearly, these are two different communities in a social network that much prefer to link to others of the same kind than to the other. But here is another such partitioning, which is just as good and completely uncorrelated with the first one. So the problem is that simply by chance, out of all the 2 to the n ways to color these nodes, there are some that look surprisingly convincing as community structures. So this is one of these areas where we really need to think about, are we overfitting our data? Are we finding things that are not actually there? I could imagine that one of these is slightly better than the other from a computer science point of view, that one of these solves a min bisection problem slightly better than the other. But again, that would, you know, yeah, who cares? I mean, there's always going to be such a thing, and even if it looks good, if there are many others that are nearly as good that share no structure with it, then you don't want to solve that optimization problem. All right. Especially if it's, yeah, even if it is. So we don't want the quote-unquote best fit. There are illusory communities even in random graphs, and of course, you know, if I show you this data and I fit it with an elaborate model, like a 10th order polynomial, I can do a really good job and completely fail to understand the data or generalize to the data I don't know. What I want is a simpler model that is willing to have a noisy fit, and that will actually generalize better to the rest of the data. You know, humans are famous for, my favorite quote is, finding black cats in dark rooms even when they're not there, right? We're excellent pattern matchers. We will find patterns even when there are no patterns to be found. So, and so will our algorithms if we're not careful. Okay, so here's a better way to choose the best labeling. So for each vertex, you want to sample all possible labelings. I'm not going to tell you yet how to do that. Maybe that's hard, but if you could, you'd want to know the probability averaged over all labelings of that this particular node belongs to this group, that group, or that group. That's called its marginal distribution, the probability that that one node is of each type. And you should assign each node, if your friend wants you to bet on types, you should actually assign each node to its own most likely label. This is called the maximum marginal estimation. Okay, anyway, so this actually optimizes the fraction of nodes that you will get right, and that's a theorem. So of course we have to be careful. If you're going to give me $1 billion if I get every node correctly labeled, and nothing if I get any of them wrong, I should do the ground state, the thing I said before was bad. But if you're going to pay me $1 for each node that I label correctly, I should do this. All right, so part of the idea is that if there really are communities, then these marginals, the fact that most of the time Jennifer is in this community, the blue community, means that there are actually many labelings in which she's in that community. So it represents a whole cluster of solutions that have something in common. Yes?
I must be misunderstanding something about the maximum marginal estimate. If your block model has some symmetry to it, for example, there are only 2 labels.
Yes, you're absolutely right. So, right. So simply by permutation, these things would fuzz out. So I'm sweeping some, so okay.
Marginal distribution, you could guarantee.
All right, we'll lift the rug back up and let this thing crawl out. So yes, we need to break the symmetry somehow if there's that kind of permutation symmetry by setting the types of a handful of vertices, for instance, or, yeah.
May I ask a stupid question?
Yes, but let me tell you my slogan. Here's the slogan. So you don't want the best solution, you want to know what all the good solutions have in common with each other. And I think the statisticians have known this for a long time, but I don't think it's really been absorbed by the vast and rapidly growing network literature. Yes?
What if I impose a cost on the number of communities as well as on every link between every bad link? Then presumably in the random case, if you jiggle the parameters correctly, the best would be just one community and you'll see that you're random. But if there actually communities are there.
I agree with you in principle. So what you're referring to is the fact that we want to penalize more elaborate models, in particular models that think there are communities there, or think there are 17 communities as opposed to only 2 or whatever. The question is what that penalty term should be. And as I'm sure you know, everybody has their favorite. So there's the minimum description language people, the what?
They have a 3-letter acronym.
Yes, there's the MDL people. There's the AIC people, which stands for the Ake-Ike Information Criterion, which is just plain wrong in this case, because it's designed for IID data. There's the BIC, the Bayesian Information Criterion, and so on and so on and so on. So each of these will give a slightly different penalty to more elaborate models. They all have you know, our best interests at heart, but it's not actually clear which one is correct in some sense. So, all right. Well, so let me proceed. So the thing is that I haven't told you. Oh, one other thing. I actually kind of said this. All right. So the total probability of getting the graph. Forget this theta thing. All right. The total probability is the log of that is a free energy, and if you remember your thermodynamics class, it has an energy term but also an entropy term. So part of our attitude is that rather than minimizing the energy, you should minimize the free energy, because what that means is that you have a model with a low energy, that means high probability, it has some good fits, but also a large entropy, so it has many ways, again, many good fits to the data, which hopefully have something in common with each other. All right, but how are we going to compute these marginals and the free energy? So, like everybody else, I used to use Monte Carlo sampling for this sort of thing, which a lot of people call Gibbs sampling, but it's too slow for our purposes. It's really rather slow. It cannot in scale to, networks with millions of nodes. Thousands, okay, but not millions. And now I'm sure there are some super sexy ways to make it run faster, but the other problem with it is that in order to obtain marginals, you need many independent samples from your Monte Carlo algorithm. So however long it takes to reach equilibrium, you need many multiples of that. And also computing this free energy, in general, computing entropies is hard with Monte Carlo. Computing energies is easy, but computing entropies, you typically need to do Monte Carlo at multiple temperatures and then some kind of integral, and never mind. So how are we going to compute these things? This brings us to belief propagation. So if you're like me, you spent several years hearing about belief propagation, hearing that it was really cool, but every time you tried to learn it, you were so snowed under by the massive density of superscripts and subscripts that it just gave you a huge headache and you decided to do something else that day. So actually for me, so I learned about this first in the context of random satisfiability and coloring problems. I like the block model because when we wrote this down, we were able to get away with hardly any double subscripts or double superscripts. All right, so here's the idea. How many of you already know the idea of belief propagation? All right, good. Well, let's tell everyone. So every node is going to send its neighbors an estimate of its marginal distribution, the probability that it belongs to each type. But with an interesting twist. When I tell Bobby my estimate, I base that on what I'm receiving from everyone but him. Similarly, he gives me an estimate based on his interactions with everyone but me. Now, there are nice principled mathematical reasons for doing this. It turns out to be equivalent to a certain variational method. But I also like this there's a nice intuition behind it, right? Which is that if I tell Bobby, hey, I just heard that there's a scientist out there who is totally unconvinced that there's going to be climate change. And he tells me, hey, I just heard that there's a scientist who's totally unconvinced. And then I tell him, hey, I just heard that again from another one. And he tells me too. Then this is an echo chamber like certain news stations where information is just being meaninglessly amplified back and forth. What we need is to bring fresh information into the conversation from outside this pair of people. All right. Once when I gave that example, someone stood up and left the room in a huff. So I hope I haven't offended anyone, or at least not too much.
It's simple. He wasn't a scientist.
Ah, yes. Well, there are a few. All right. So we pass these messages back and forth until we reach a fixed point. We might fail to reach a fixed point. It might never converge. If we reach a fixed point, it might be a terrible estimate of the marginals. There is a big warning label here saying exact only for trees. And then there's an asterisk saying maybe asymptotically exact some of the time if the network is locally tree-like. But actually, that's a major area of active research. But if it works, this fixed point returns these marginals and something called the beta free energy, named after Hans Bethe, who also figured out what makes the sun shine, which is when it works, a good estimate of the free energy. All right. So let me just show you this, because it's not 5 o'clock yet. I think you can parse it with a little help. This is just a normalization. Okay. So this is what I tells J about the probability that I is in group S. This is just a prior probability that you're in group S that I didn't tell you about before. Then there's a product over all of I's other neighbors that, for instance, if they tell I that their group R, well, because they are connected, then we're going to have a weight here, P sub RS, which is the probability that they're connected. Then remember, there are also these messages coming in from your non-neighbors because you do interact with them, right? But, okay, the fact that this is a product of a sum and not a sum over a complicated joint distribution is this thing called conditional independence. So we're assuming that conditioned on I's state that its neighbors are independent from each other, that they're only correlated to the extent that they're communicating through I. And this is why this is exact only on trees. Now, maybe these guys are connected by a long path and maybe correlations decay quickly as a function of distance. But then again, in lots of real networks, there are a ton of triangles, so they could be connected directly, in which case this seems like a completely loony assumption. It works surprisingly well in practice. All right. Now, there's a problem here, though, which is that everybody's talking to everybody else, whether they're connected or not. And that's not scalable. N squared today, in this context, is not scalable enough because maybe n is 1,000,000, and 1,000,000 squared is too big. So happily, if we use the sparsity of the network, if we assume the network is sparse so that these p's are small, we can kind of wrap these terms up. One way to view this is to say, I will carefully tailor my message to each of my neighbors, but to all of my non-neighbors, I will broadcast the same message. Okay, good. Now the number of messages we need to compute and update is only proportional to the number of nodes and edges, which makes it scalable. Now it's scalable. Okay, for some people, even this isn't scalable, but for me, this is, I'm going to stop here. All right. Now, of course, there's a question of how long this will take to work. But let me just show you a few pictures. Here are some common examples that people like of the block model. Here's one where you have one probability Cn of connecting to others in your group and another outside your group. Here's a nice example where maybe there are core nodes that connect to each other with high density and then with low probability to nodes out in the periphery who connect to each other with even lower probability. And then there's graph coloring where you only connect to those with a different color from yourself. All right? So here's our hydrogen atom, our fruit fly of network science, the Karate Club. Has anyone not heard of it? Okay, are you serious, Madhu? Give me a break. You're going to make me tell the story? University Karate Club, 1977, a young anthropologist named Zachary interviewed everybody to find out who they were friends with. By the way, this is back when friend was a noun. And then there was a big argument between the president and the instructor, which I suspect Zachary fomented this argument in order to have a good thesis to write. They broke up into two factions, and then he said, gee, can I retroactively guess what the factions would be based on the friendships? He used max flow min cut and got everybody right except for one guy who was friends with the president, but he stuck with the instructor because he had a black belt exam coming up in 3 weeks, and there's a whole page in the thesis about this. All right. Now, of course, we shouldn't view this just as a failure of the algorithm. It's a
time that karate clubs were male only, so it's not males and females.
Oh, okay. Well, I don't. Is that true?
No idea.
I don't know. I don't think it was male only. I don't know. So, and we should remember that whenever we see a network, there's lots of idiosyncratic, real-world facts about the nodes and edges that are not drawn in this graph. So, anyway, we shouldn't expect to get everybody right. So, here's our two factions. But the funny thing is, the block model, the vanilla block model that I've told you about, actually prefers this structure. You tell it, okay, there's two kinds of nodes. Go and find them. And it says, oh, okay. And it comes back and it says, hey, I found there are two kinds of nodes. There are high-degree nodes in the middle and low-degree nodes on the outside. Did I get it right? Huh? And you're like, well, that's not what I wanted, but it's not wrong. It is also true. Both of these types of structure are there. And so one thing we can do, which is kind of fun, is take a slice through the parameter space, the model space of all these block models, and actually look at the beta free energy, except I've turned it upside down so that up is good. And we can really see that both these structures are there as kind of local optima in the space of models. I think that's kind of a nice thing to be able to do. All right, we can also see as the model learns more how it switches from one to the other. So suppose you're the algorithm, and for $1, you can point to any node you want, and I will tell you its true type, but you have to figure out which node to point to. So you want to learn about the nodes that will teach you the most about the rest of the network. So we did actually a kind of slow thing with Monte Carlo, and we figured out which node had the biggest mutual information between it and the rest of the network. So which would literally give us the most bits on average of information. So it starts out with this high-low degree, but like any of us would, it says, oh, you know, what's the type of that node? We tell it it's red, and it says, oh, okay. All right, I see that there must be two groups here, but I'm not sure where the boundary between the two lies. So tell me about this one. And now, I kind of like this. We did not tell it to first ask about the hubs and then about the boundaries. We just said maximize the mutual information. And so after asking about just a few nodes, it labels most of the nodes correctly. All right, so belief propagation has this nice, I think, double role to play. On the one hand, it's an algorithm that you can run on real networks, and it's pretty fast. But you can also try to analyze it using methods from physics or rigorous methods from computer science and probability theory, and try to do things like compute analytically, well, what fixed points is it going to have? And are these fixed points stable or unstable? And this will reveal these phase transitions that I want to tell you about. So here is a graph. Let me explain the graph. Remember that C in, C out thing. So this axis is their ratio. At this end, you only connect to others in the same group. Here, you connect everybody equally, so it's a completely random graph. This axis is the number of iterations that belief propagation took to converge. So two things to notice. One is that for each value of this ratio, the number of iterations we needed for 10,000 nodes and for 100,000 nodes was about the same. Now you can prove that you need that in some cases you need the number of iterations to grow at least logarithmically. Elchanan and Allan taught me that because I was going around claiming it was a constant, and it's not. But it doesn't, numerically, we don't see it very strongly here. The other thing to notice, so I mean, that's good, it converges quickly. But the other thing to notice is that the convergence time explodes at a particular value of this ratio. So to a physicist, this is a sign of a phase transition. Whenever things get close to their boiling point or their melting point or any other sort of transition, times to equilibrium diverge. You get bigger fluctuations over larger scales, and it takes longer for things to settle down. So indeed, here is that transition. The x-axis is the same. Now the y-axis is the accuracy, the fraction of nodes that we label correctly with what a random coin flip would do subtracted off. And the interesting thing is that as you move towards this structureless graph, you might expect that this would go to 0 gently, but instead it crashes down to 0. So here, when you're still 50% likelier to connect to others in your group than to others outside your group, the algorithm isn't labeling the nodes any better than a coin flip. So what's going on? So in a physics paper, we non-rigorously said, you know, we'll bet that not only can belief propagation not work here, we'll bet nothing can work. No kind of algorithm can work. And it took me a long time so this, you know, the idea of this kind of transition was taught to me by Lenka Zdeborova and Florent Krzakala, because they have enormous amounts of experience in this sort of system. And at first I thought that they meant it's exponentially hard, but it turns out that's not the issue at all. So let me explain what happens. Here, let's assume that there's this symmetry, you know, let's see. I mean, if I tell Bobby, hey, I'm equally likely to be in the red group or the blue group, and if everybody is telling Bobby that, he compiles the results and says, hey, I'm also equally likely to be in the red group or the blue group. So there is a trivial fixed point where all these marginals are uniform. The question is, when is this fixed point stable, right? So if it's globally stable, then no matter what initial guesses we start with, we get sucked into it, and then we're just doing no better than chance. On the other hand, if it's unstable, then hopefully, even if we start nearby it, belief propagation will move away from it and create accurate biases. So this point here is exactly the point where it becomes unstable. So this was proved by Mossel, Neeman, and Sly, and then they and independently Massoulie proved the positive result as well, that on this side, you can label the nodes better than chance. But it's only been proved in the case of 2 groups. For more than 2 groups, you might think, oh, well, it's just more technical, but it gets more complicated. Yes?
There's something I'm unsure about on the previous slide.
Yes?
There's also some value of C out over Cn where it becomes information theoretically impossible to...
That's what they proved. I'm sorry, I'm starting to speak more quickly, but that's what they proved. So think of the graph as a kind of a communication channel, right? I have these underlying labels for the nodes. Then I probabilistically generate this graph. Then I show you the graph, and I hide the labels from you. So they showed that it's information theoretically impossible to recover the labels from the graph. So they actually showed 2 things. They showed that the real marginals are asymptotically close to half-a-half. But they also showed that the distribution of graphs you get from this model in this regime is contiguous with the distribution you would get from an Erdős-Rényi graph of the same average degree. It's not that the total variation distance is small, it's not, but contiguous means that any high probability event that's true in one is true in the other. So there isn't even an algorithm that will turn on a green light saying there are communities that is right with probability close to 1. Okay.
All of this was pre-shadowed a little bit by work by Dimitri, right?
Well, and maybe
and
some of
you
it with
actually-
Chris.
On set, where sort of a similar phenomenon happened that you couldn't distinguish it from a random graph?
Well, I would say that this was Dimitris and Amin who first, in that context, pointed out that the planted ensemble can be indistinguishable from the random ensemble. Yeah. All right. Okay, so here's something that badly needs to be proved, about which almost nothing is known rigorously. So when we have more groups, it turns out that there isn't just this detectable versus undetectable. There's another transition. So here, this is a hidden 5 coloring. So I have 5 colors of nodes, and I've added random edges, but only between nodes of different colors. Now, and this is the average degree of the graph. When there's a lot of edges, you can find the coloring quite accurately. When there are few enough edges, then you can't do anything. But in between, there's an interesting regime. In this regime, there are, well, from here to here, there are at least 2 fixed points. The silly one, where everybody's equally likely to be in every group, and an accurate one, okay? So the trivial one is locally stable, but not globally stable. The problem is that the basin of attraction, the set of initial messages which will lead you to the accurate fixed point, appears to be exponentially small. So you have to be exponentially lucky to find it, or have exponential time to explore the whole space. So in this regime, we believe that finding the communities, and you get similar things in other areas of the model, we believe that finding the communities is information theoretically possible, but exponentially hard. Now, of course, we don't know that P and NP are different, but we could still hope to prove that certain classes of algorithms, like belief propagation, have exponential difficulty with this. Like we could try to prove what I just said about the basis of attraction. There is yet another transition that happens there, where in this region, we believe there are exponentially many fixed points, and all of them are locally stable, and you would have really no reason to choose one over any other. Okay, now, this is one of these places where we start late but end on time, right? I hate that. All right, so now, of course, I can find this point if I have some initial hint, like some metadata, okay? So I don't know if you heard that quote.
You can have a little more time.
Oh, okay. I don't know if you've heard that quote from the former.
Is 5 is 50,000? Can you tell the difference?
What?
Go back.
50,000 groups?
Colors.
I think that regime would get really big there because, like in the coloring problem, right? You have a huge.
Can you rigorously prove that now, since it's so big, can you actually distinguish it rigorously?
In that regime, this does start to bleed into some work by Amin Kojoglan and his collaborators on a hard but colorable region. Yes, so you could prove some kind of, you could probably prove like a clustering result, or as they like to call it, a shattering result.
Exactly. So you say probably nobody has really done it.
I don't think people have done that in this so-called positive temperature regime, but I expect you could. Yeah. All right. So what if I give you the correct labels of a certain fraction of nodes? That should help you label things, right? And indeed, you have some nice additional phase transitions everywhere, where your accuracy suddenly jumps when I give you a certain amount of information. And I think of this as a kind of percolation. If I tell you about only a tiny fraction of nodes, well, you know them, you can make good guesses about their neighbors, maybe their next nearest neighbors, but it decays. But if I tell you about enough, then your knowledge of the network percolates and becomes global, and you can make a good prediction about everybody. And here's a picture of that. Here's this discontinuity, which decreases until it reaches a second order phase transition here, beyond which everything is smooth. And none of this has been made rigorous. So all of these are these cavity method calculations that we can do numerically. I think that they're exact, but I don't know.
So does this also influence the two-coloring case, where I thought there we said...
Right. With only two groups, this doesn't happen. So with only two groups, when I give you a little bit of a hint, the transition just smooths out. It goes from this to a smooth curve.
I see, all the way.
This phenomenon only happens when you have more groups and you have that hard but detectable regime. So, yeah. Okay. You can add more data. You can throw in text classification using classic models of text like LDA, and then you can try it out on a network of patents, and you can get this cool looking division of patents into the arithmetic instructions and the debugging stuff and the power supply stuff. And as you can imagine, you get a better classification than if you use only the links or if you use only the text. By combining the two types of information, we do a better job. All right. Finally, here's a very pretty picture, which I just had to show you. So we just got published. This is work of my postdoc, Pan Zhang, who is looking for a job. And it just got published in PNAS, or accepted, so give him a job. So what we do here is we start with the network, and we're going to recursively subdivide it, but only as long as belief propagation is telling us that there is statistically significant structure. As soon as it tells us that there isn't, we stop subdividing. And we can do this very quickly. This is another classic network of political blogs. So there's 1,000 nodes. And again, we're not trying to optimize the structure. We're trying to find out what many competing what many good community structures have in common with each other. Now, I'm very sorry to tell you that these blogs, which were about the 2004 political election, it's a tragedy, but what they were actually saying has apparently all been lost in the mists of time. But I like to think that if we could find it, we would find that these are the, Labor Democrats, these are the anti-abortion Republicans, and so on, that these are divided out by, so these are the Democrats, these are the Republicans, but that they're divided out by topic in interesting ways. Okay. I'm of two minds about whether I should do this. I can do it in 5 minutes. Want me to do it in 5 minutes? Okay. So, let me tell you about what at first appears to be a completely different approach, but is deeply, deeply related. Yes, sir?
Just a quick question. So about the last slide, which was, what determines the connections between blogs? Like what determines an edge?
Oh, these were just links. I think that, whether this blog linked to that blog,
It's just like
whether they reblogged or whatever you do. Yeah. There's some way for blogs to blog each other. I don't know, actually. Yeah. I'm a theorist, so I'm not sure how this works, actually. Okay. Okay, so you guys work with computers, right? You know about some of this stuff?
And just so, what do you do? Is it reblogging?
I'm the social media person in the room. That's why they're laughing.
So
give us the answer.
So you know about all this bloggery.
For once, in the last 59 minutes, yes, I am on solid footing. Yeah.
Is it reblogging when you blog someone's blog?
Yes.
It is. It's reblogging.
Yeah. Yes. Yes.
It's
reblogging.
Okay.
As long as there's a hyperlink there, that's when it's reblog.
Right, the hyperlinks.
Yes.
Yes. I've heard about those too.
You can follow.
Right.
Okay.
If you click on it with your mouse. See? I'm hip.
You don't have a mouse anymore if you're hip.
There's no Okay. All right. Okay. So let me tell you about what at first appears to be a totally different family of algorithms, but is actually connected. So another very popular method, because it's very fast, because sparse linear algebra is very fast, is to take your network or your graph and to associate a matrix with it, like the adjacency matrix, where you have a 1 or a 0, depending on whether there's an edge there, or if you prefer, you can take this thing called the Laplacian, or you can take the adjacency matrix and normalize it, so it's like the probabilities of a random walk. Everybody has their favorite. People argue about which is best. And then you take the nodes, and each one corresponds to a component of, for instance, an eigenvector. And so here is our Karate Club network again, where I've labeled nodes according to whether the second eigenvector is positive or negative there. And you can see it does a nice job. And if you have k groups, you look at the first k eigenvectors and then use your favorite clustering algorithm in k-dimensional space to give a picture of where the nodes live. Okay, so when does this work? When does this succeed? So in a lovely paper in physics, which again I think is not quite rigorous but almost certainly correct, Rajnata Kuditi and Mark Newman computed the typical spectrum of a graph generated by the stochastic block model. And so, as some of you know, random matrices often, if you look at the density of their eigenvalues, you get this beautiful thing called the Wigner semicircle. Drop everything and learn about it. There's 8 different ways to prove it. It's very beautiful. But there's also these eigenvalues outside this semicircle. So we call this the bulk, because in here there's lots and lots of eigenvectors that look pretty much random. What you want is to find this eigenvector, which is actually correlated with the communities. So as you vary the densities of within group and between groups, at a certain point this crosses into the bulk. And at that point, if you ask MATLAB to tell you the second eigenvector, it gives you one of these, and you look at it as totally random, and you don't learn about the communities. And happily, this happens at the same detectability transition that we had earlier computed using belief propagation, which I think drives home the fact that that transition is an algorithm-independent phenomenon. So I really like that. But there's a wrench in the works, or as my parents would say, a squirrel in the junction box. They eat the wires. The problem is that for sparse networks, this semicircle doesn't hold anymore. And one reason is that in sparse networks, imagine that you have somewhere a high degree vertex. So if you apply the adjacency matrix twice, if this thing has degree d, there are d ways to leave and come back, which if you think about it means that there's an eigenvalue there which is at least square root d. So if there's a couple of high degree hubs of degree 100, then there's going to be an eigenvalue at like 10 way out here. And so when you ask your spectral algorithm to tell you about the communities, it tells you about these high degree hubs instead. And that's not what you wanted to know. So in the sparse case, we have these big deviations from the semicircle law. We have these things bleeding outside here and swamping the eigenvalues we care about. We must fix this. How can we prevent this nasty backtracking? Well, it sounds a bit like that echo chamber before, right? But now it's between one newscaster and all their Twitter followers. So we will prevent backtracking. So let's just take a walk on the directed edges of the network, and let's not allow you, me, any of us, to turn right around and go back the way we came.
But then we get stuck.
No, because we can go here and then go there and then go there.
I see. If it's a tree, we get stuck.
If we get stuck at the leaves. Stay away from the leaves. All right, now this matrix is not symmetric, so its eigenvalues now live in the complex plane. But now notice how this is the same matrix as I showed you before. Now it's very nicely confined in this disk whose radius is square root the average degree. So, and I learned about this from Elchanan and Allan, who had seen this type of, so they and their student Joe Newman and I and my other co-authors, we got together on this and published this paper, conjecturing that that the spectrum is confined in this disk. And indeed, this then crosses the disk and gets lost at exactly the detectability transition.
So this is like a generalization of the semicircle, a variant of the semicircle.
Yes, right. So this is known for deregular graphs. We're arguing that it's true based on average degree in the stochastic block model or in GNP. That's the conjecture. Here is a much better picture. It looks like a scary pumpkin or the eye of Sauron, which I had to rotate 90 degrees. Okay. All right, so indeed, all the classic methods of spectral clustering fail some distance away from the detectability transition. Spectral clustering based on the non-backtracking matrix goes all the way down, and indeed does almost as well as belief propagation. So this is interesting.
So is that saying that that's kind of the only way that the spectral methods are failing, or is it just that you've only considered particular,
there are multiple ways for them to fail.
Right.
So the stochastic version of the adjacency matrix, its problem is not high degree vertices. Its problem is rattling around in the little trees that dangle off the giant component and sticking around in them for a long time.
Yes.
Or getting stuck wandering back and forth on the occasional long path of degree 2 vertices. Now, there are other fixes. So Arash Amini and Lisa Lavina, and I can't remember the other authors, they looked at another type of regularization which kind of adds a teleport term. So it lets you get away from these localized structures. So it has a tunable parameter. It's not clear how to set it, but that seems to help as well.
So it's kind of like the jump that you would have in a,
in PageRank.
In PageRank.
Back when PageRank was what we tell our students it is.
Hesitating to find the Microsoft correct.
But
it's
yes, right.
No,
Okay.
but so it's okay, or it's like a lazy random walker. It's something that'll
not lazy.
smooth, not lazy.
A random walk with teleportation.
With teleportation. Yes, okay.
All right, so
the title of the paper? The last slide.
the title is Spectral Redemption. Elchanan came up with that.
That's pretty good.
All right. Okay. So what's the connection? Well, the point is that, remember, the detectability transition happened because of the trivial fixed point becoming stable. Well, you look at the matrix of its derivatives around there to tell whether it's stable or not. So you linearize, you expand to first order the belief propagation update equations around that fixed point. And those derivatives are essentially the non-backtracking matrix. It's actually that with a tensored, with a little matrix, which we can ignore. So that is how we stumbled upon the non-backtracking matrix. Just by saying, well, let's use that matrix that showed up in the question about whether or not the trivial fixed point is stable. And it had appeared in the literature before. All right, morals. So these generative models like the stochastic block model, they're really nice. I'm a kind of moderate Bayesian. Any frequentists here? Okay, so I like it because you're required to write down a guess about how the presence or absence of links depends on hidden attributes of the nodes, and I think it's good to try to write down such guesses. All right, not that they'll be right. But hopefully they'll help us some of the time. But the most likely labeling, the ground state, often overfits, producing illusory communities where there are none. So instead, you should seek the consensus of many good solutions rather than the quote-unquote single best one. To do that, you need to compute marginals, and belief propagation will do that, at least some of the time, quickly. And it also gives you this thing called the beta free energy, which lets you explore the landscape of possible models. And it is also our favorite way to choose the number of groups. So we can talk more about that. Basically, as you add more groups, the beta free energy improves to a certain point, but then it levels off. We can also study belief propagation analytically and look for these phase transitions in our ability to find communities. We can extend it to fancier models with different kinds of data on the nodes and edges. And sometimes it even inspires new operators for spectral clustering, connecting these two families of algorithms. I'm really over time, but I just want to say there are lots of interesting cultural gaps here. Some of my best friends are machine learning people. And often when you read those papers, the models are extremely elaborate with lots of parameters and lots of priors and hyperpriors and hyperpriors and so on. And it seems rather difficult to fit them to the data, although then people come up with various high-powered, clever ways to fit complicated models to data quickly. I would rather fit a really simple model to the data. And I would rather do this even if their model gets 86% accuracy and mine only got 83% accuracy. Because at least I have some sense of what my model is doing and when it works and when it doesn't, and I might even be able to prove things about its strengths and weaknesses, which I think is valuable. Of course, it's also valuable to push to 86, but I like these simple, elegant models.
So you claim that belief propagation just is 2% worse than deep neural nets?
We're running out of time, Christian, I'm sorry. All right, so, but finally, a cautionary tale, which I'm obligated to say, okay? Networks as a field is, I think, as we all know, a bit too popular for its own good. And in particular, the naive topological modeling of networks is a bit too popular for its own good. Here is an actual blackout. After big blackouts, people do a careful analysis, like with airplane crashes, okay? The network literature is filled with papers saying, well, blackouts travel from nodes to their neighbors, right? Like an epidemic. Well, actually, that's not how the power grid works at all. So this power line went down, and then that one, and then that one, and then this one, hundreds of miles away, and not even topologically close, was the next to go because of the way the flow of electricity through the network reorganized itself at the speed of light. It's a very non-local process. So I say this because it's important to remember that this topological picture of networks often ignores a lot of important real-world dynamics. Every metaphor has to pay its own way, right? So in the 19th century, everything was a steam engine, and then everything was a computer, And then in the 90s, everything was an economy, like even the brain, even like neurons in the brain are an economy. Unless you're kind of more earthy, crunchy, then everything's an ecology, because then there's symbiosis and mutualism, and that's much nicer. And nowadays, everything is a network. So each of these metaphors makes certain aspects of the real world easier to see, but may obscure others. Thank you very much.
You did say that there was this thing using marginals, which is likely to be more robust. So do we have any sort of evidence of that, or is it just a belief?
Well, we certainly have things we can point to where the ground state is a bad estimate and this marginal approach is a good estimate. But there is also a theorem from Bayesian inference that if you want to maximize the number of variables that you get right, you want to use the marginals and not the ground state. You know, on the other hand, computing them can be difficult. So because it requires some kind of sampling or exploration of the space, but sometimes belief propagation does that very well. When it doesn't, you can always fall back on Gibbs sampling, which will always work if you give it enough time, but that might take a long time. Yes?
So I sort of have good intuition for what a phase transition means in the context of networks. So if you have like a Facebook network, you just like give an example of when phase transition would happen.
So let's suppose you have a community of people, and I know there's some controversy about whether we mean so-called annotated communities or structural communities, but let's say you have two groups of people. And they really do link to others in their same group with probability twice as big as, you know, outside their group. But if the network is too sparse, then indeed, if you're not given any of the metadata, if you're really just trying to cluster them based on the topology alone, there's a regime in which you just can't. Which, you know, put that way, maybe that's not so surprising, but you know, this hadn't been observed or discussed before. And I think everybody knew that, well, if I connect with those in my community with probability 1.001 times the probability I connect outside it, fine. But actually this can happen when that ratio is 3/2 or 2. I mean, one way to view it is that in a really sparse network, if people don't have that many links, and I know on Facebook people tend to have a lot of links, but a lot of friends. But in a sparse network, if everybody only has a small number of links, then by chance, some people might have more links outside their community than inside their community. And that is one reason the algorithm gets confused. So you can view it as a theoretical result saying sometimes you really need the metadata. And then I think this gets into interesting questions like, what if obtaining the correct metadata is costly? What if people have some demographic attribute that they don't want to tell you, or some of them left it blank, or some of them want to lie about it? And maybe you can discover its true value by offering them a coupon or getting a warrant from a judge or something. And you know, then the question is, if that information is costly, which nodes or which links should you really examine closely? Which ones will teach you the most? Which gets into this nice active learning question.
These clustering problems seem like they're quite hard. And another sort of related problem would be understanding the process that generates the network. And that might be a low-dimensional parametric process that might be a lot easier to learn about than the classification problem, right? I mean, if
you give me the real labels and the links, then yeah, from that I can very quickly
but
fit
also
a model.
I didn't quite. I mean, so I have this. So the link I'm thinking about is the linking to sort of the Gaussian mixture model thing, where we sort of know that it's quite hard to sort of pick out, classify every point as being one or the other, but
right.
I can somehow still learn about the mixture process.
Yeah, although there are interesting, you know, if you have a mixture of two Gaussians that are too close together, it's really hard to tell them from a...
No, but this is an information theory, not computational.
Yes, I agree. Well, and so is the first detectability transition I showed you. So the case for two groups is really an informational theoretic question. So, I mean, going back to your question about what does this have to do with Facebook, if I zoom out a little farther, I would say that there are a lot of algorithms out there that claim to find communities of various sorts. And when you hook them up to nice visualization tools, it always looks really beautiful. Well, beware. And some of the things that these algorithms are showing you are not actually there. And just as statistical significance is a huge crisis in biomedicine right now, where we're discovering that many of the effects that we thought were significant aren't, because of publication bias and so on. Well, I think there's a similar issue with any sort of data analysis, including network analysis. So.
Let's thank Chris again.
Thanks.